All right, so in this video, we'll be talking about Gaussian elimination with pivoting. The last video, we covered Gaussian elimination without pivoting. Kind of one way you can view the difference between this video and the last is that in the last video, we talked about Gaussian elimination. But in this video, we're going to talk about Gaussian elimination with partial pivoting. Right, so this was our second version. And then we also have Gaussian elimination with complete pivoting. So we'll also mention that in this video and talk about it. So the first thing to address about pivoting, or why we need to pivot in general, is, as I mentioned in the last video, that Gaussian elimination is not well defined for all invertible matrices. And so one example of this, right? So if I give you the matrix A, this is probably the simplest one, 0, 1, 1, 1. You could show that there's no way that you could find an L and a U, a lower triangular and an upper triangular matrix that would multiply to give this A. It can't be done. The reason kind of why is because now when I look at the first column, that component that I said that I would need to basically be dividing by to compute those M matrices that we talked about in the last video, it's already 0. So we essentially can't zero out everything except the first component because it's already 0. And so that's why we have to do pivoting, right? And so if you were doing, say, Gaussian elimination, you probably know from maybe Math 22 that you can swap rows. That's another operation that you can do that doesn't change the solution or the solution space to the linear system. You will have to permute the right-hand side vector as well, but you can do this. And so what you might have done in 22 is you introduce a permutation matrix. I'm going to call it 0, 1, 1, 0. And what this permutation matrix does, you can kind of stare at it and think about it. It will swap the first and the second row of when I multiply on the left, right? So if I take PA, what this permutation matrix does, maybe let's write it out. We'll get 0, 1, 1, 0, and then times 0, 1, 1, 1. And the result is it just swaps the first and the second row. So we'll get 1, 1, 0, 1. Right? But now, if I look at this matrix, this is very easy to do the LU decomposition of. Right? The reason why is because it's already upper triangular, just incidentally. Which means that I can say PA is equal to, I have that upper triangular matrix, 1, 1, 0, 1. And then what would go on the left? Well, the identity, because it doesn't change anything, and it's also lower triangular. Right, so this would be my L, and this would be my U. So this is a very simple example of a matrix for which Gaussian elimination without any pivoting, so what we talked about in the last video, is not well defined, but Gaussian elimination with pivoting. So in this case, this is an example of the Gaussian elimination with partial pivoting algorithm. This output would be something you would expect from, say, GEPP. This PA is equal to LU factorization that we just found for the matrix A. So that was an example of a very simple matrix for which you actually have to do pivoting theoretically to do the LU decomposition. Right? The process is not defined standard Gaussian elimination without any pivoting. You'd have a division by 0, or you wouldn't be able to find these L or these U factors. Now, there's actually a more pernicious type of problem that arises in, say, computational math or numerical and algebra, which is I might not have zeros, say, due to floating point. I might have something that's very close to 0. And in this case, you might actually still need to pivot to guarantee accuracy in your solution. Even though the pivot may not be exactly 0, if it's very small, what we'll see is that this will cause possibly blowing up of the entries in the computed LU factors, such that when I multiply the computed factors out, they no longer equal A to any accuracy, or possibly just has a very large error when I compare it with A, which doesn't make sense, right? Because I compute these factors and I multiply them out, by definition they're factors, so they should multiply to be the thing I said that they're the factors of. So here's a very simple example of what I'm talking about. And so here, this is due to Forsyth and Moeller in 1967. This is an example that they presented, which was, I'm going to assume that I have a 3-digit accurate arithmetic system. So what this means is that I can compute floating point operations accurate to only 3 significant digits, right? And so now I'm going to ask, okay, let's compute the LU factorization of this matrix A, which is invertible. And so what we'll get if we apply Gaussian elimination, so I'll just say GE will produce an L tilde. So it will say that A is equal to this computed L times this computed U. And what happens is that this L, you'll see that it's equal to 1 over 10 to the 4th, 0, 1. And this U, in exact arithmetic, this is wrong, but if you follow this 3-digit accurate arithmetic system, what you'll see is that this computed U will be 0.00011, 0 minus 10 to the 4. Okay? Right, so this is kind of simulating the fact that we work in a floating point system. I'm saying the accuracy that I can do these floating point operations with is I can get it up to 3 digits. So now you might ask, well, I've computed L and I've computed U in A is equal to LU factorization using Gaussian elimination. So let's multiply them back out and check, does it equal A? So what we see when we multiply it out, and again, we're still using our 3-digit arithmetic system, what we get is we get 0.0001, 1, 1, and then 0 in the bottom right. And the thing to know is that this is very obviously not equal to A. Why? It's because of this 0, right? So that entry was actually originally 1, but when we compute it with this 3-digit system, we get something that's completely wrong. And so we might think about, okay, why did this happen? Well, it's because when we look at A, the pivot, the very first pivot, or really the only pivot that we care about, was very small, right? And so let's kind of play a new game. So we're going to, instead of doing Gaussian elimination, we're going to do Gaussian elimination with pivoting, where before we actually do the LU factorization, we're going to interchange the first and the second row. Right? So what I mean is that I'm going to kind of introduce that same permutation matrix I talked about at the beginning that's going to swap the first and the second row. So this P times A, I'll call this new matrix A prime. And what it looks like is it looks like 1, 1, 0.0001, 1. And so what did I do is I swapped I basically swapped the rows of the matrix such that the pivot was 1, which is bigger than this tiny 0.0001. In general, when you do Gaussian elimination with partial pivoting, here there was only one choice to make, right? Because there are no more rows. It's a 2x2 matrix. In general, Gaussian elimination with partial pivoting, or this GEPP, you will swap the rows of the matrix. You'll swap just 2 rows such that you bring the largest entry in that column. So, right, because when I look at the first column, I'm going to look down that first column and find the entry with the largest absolute value, and then I'm going to swap the rows of the matrix such that I bring that up into the pivot position. Right. So here there was no choice to make, but in general, you will look down the column of the matrix that you care about at that iteration, and then you'll pick the largest absolute value entry and then swap the rows to bring it into the pivot position. Okay. So what effect does this have on the calculation? Right, so now I'm going to go through the same process. I'm going to compute, I'm going to call it L tilde prime and U tilde prime. And what are these now? And I'm computing these, so these are the computed LU factors for the matrix A prime now, right? Not A. This is A with the swapped rows. And so what do I get now is I get 1, 0, 0.0001, 1, and then I get 1, 1, 0, 1. Right. All right, so now let's play the same game. So let's multiply it out and see, does it equal A? Right, and so, or does it equal something at least that's close to A? When we did Gaussian elimination before without the pivoting, we got something that was very far apart. But this is going to give us 1, 1, 0.0001, 1.0001, which is very close, right? I mean, it's accurate except for this up to, say, 0.0001. That's the only entry that's different from A prime, right? So we would call this a good result. And so what did we just observe? What we saw is that when we did pivoting, we actually didn't get any error in our calculation. At least of, we did get an error, but it's just very small compared to what we did when we did not do pivoting, right? So when we did not do pivoting, we actually just got 0 in that entry compared to the corresponding entry in A. Right, so the goal of doing, or the reason why we introduced pivoting is to avoid division by very small pivots, which can cause the entries in L and U to grow to something very large, such that when you multiply it out in finite precision arithmetic, you could get a very different answer than A, right? But here this is just a simple, it's not a proof, but it's a simple example showing you that by pivoting, you're able to kind of control the growth of, and we'll introduce the growth factor in a minute. You're able to control the growth of the size of the entries in the computed LU factors, such that when you multiply them out to ask does it equal A, the error is not too bad. So that's kind of that's the reason why you would do pivoting, even if you don't have a 0 pivot, is because a small non-zero pivot can really harm the accuracy in your computed factors. Okay, so we might ask, so like, what is the problem, or why does Gaussian elimination give us these poor results without pivoting sometimes? And so there's a theorem that we could state. We're not going to prove it, but so there's a theorem that states that Gaussian elimination, the produced L and U factors, right? So remember, we use this tilde to denote what is the one that was actually computed on the computer. The computed LU factors, they satisfy L times U is equal to A, the thing we want, plus some error matrix. And what's true about this error matrix is that I can bound its norm. So, right, remember we talked about matrix norms right at the beginning of the class. I can bound the matrix norm of E. It's going to be bounded above by n times machine epsilon. Right, so we talked about that as well. It's like the relative accuracy that you can apply these standard floating point operations with, times now the norms of these L and these U matrices, right? And remember, we just had this discussion about why is it possible that these the entries in these computed LU factors can begin to blow up if we ever divide by a pivot that's very small but non-zero. And so what this upper bound tells you is that this error could actually be as large as this upper bound. You have no guarantees. It might be a lot smaller, but in the worst case, it could even maybe attain this upper bound. That depends on possibly something very, very large, right? So as the entries of L and U grow, so will these two norms, right? That's kind of the relationship. Yeah, and so that's kind of the problem, is you're unable to prove what we would want to prove, which is backward stability for Gaussian elimination. You can't prove that. because it's not true. It's not a stable algorithm. So one thing that people have come up with to try to quantify this growth of the entries of the computed LU factors is called the growth factor. And so what the growth factor is it's the ratio of the largest absolute entry to any of these intermediate matrices, right? So this A0 is equal to A, right? Just the original matrix A. Now this A1 is that intermediate matrix that was M1A, right? And then so on, right? So if I look at any of these intermediate matrices, I take the largest absolute entry across all of them, and then I divide it by the largest absolute entry of A, which is the matrix we started with. That's the definition of the growth factor. And just to kind of throw back to that example I showed you earlier in the video, where we had this matrix A, if you want to compute the growth factor of Gaussian elimination applied to that matrix, you would see that it was 10 to the 4. Because in the original matrix, the largest absolute entry was 1. But then we actually ended up with an entry of negative 10 to the minus, or negative 10 to the power of 4 in I think the L factor. Now, for when we pivoted that matrix, so we interchanged the first and the second row, what we saw is that we didn't have that same growth, right? And we actually had pretty accurate, when we multiplied L and U out, it's pretty accurate relative to A. And so if you computed the growth factor for that, you would have rho is equal to 1. So that's kind of what's going on with the growth factor, is it's trying to quantify how large are these entries getting as you move along with Gaussian elimination compared to the original matrix A. And I mean, ideally, we want to keep the growth factor small, right? Because that will help mitigate these problems with these errors in the computed LU factors. There's another theorem, kind of related, analogous to the one I just showed you for Gaussian elimination, but this one is for Gaussian elimination with partial pivoting. And so the idea is Gaussian elimination for partial pivoting will produce again, an L and a U factor, such that, again, LU is equal to A plus some error matrix. But here now, we actually have a different bound on the error, this error matrix. And now what this error bound involves is it's in terms of the infinity norm, and it's less than or equal to n cubed times some growth factor dependent on n, times machine epsilon, and then times the infinity norm of A. So the big difference now is that it doesn't depend on the computed LU factors. It just depends on the largest, remember that, or it depends on the infinity norm of A, right? And so this is something that won't grow, or is not dependent on, say, dividing by pivots that are close to 0 and whatnot. It's just it's a fixed number that is we know in advance, or we could compute. Now this growth factor, right? So we want to keep the growth factor small. That's what's going to help us keep accuracy, or at least ensure that this error bound, this upper bound on the error, the infinity error, the infinity norm error of E. Essentially, we want to keep the growth factor small. But one thing that you can prove for Gaussian elimination with partial pivoting is that the growth factor is bounded above by 2 to the power of n minus 1. And so this is kind of a good thing and a bad thing for Gaussian elimination with partial pivoting, is it doesn't depend on the norms of the computed solutions, but instead it depends on something that's exponential in n, right? So our growth factor, in the very worst case scenario, it could be as big as 2 to the power of n minus 1. Now, I'll just tell you, this is theoretically bad, but in just vast experiences, many years of experiences, people testing different matrices, whatnot, the ones that come up in practice, you will rarely ever have a problem with. You'll never see the growth factor actually get as large as 2 to the n minus 1. Almost always. Now, there are just analytic examples, a few examples that you could come up with where you actually do achieve this upper bound for the growth factor. But these are kind of like contrived examples that are very rare. So in practice, you would say that Gaussian elimination with partial pivoting is stable because of this result I just showed you. Although in reality, like if I consider all possible matrices, there are matrices for which it's not backward stable because it does actually achieve this this upper bound on the growth factor. So practically it's stable, but theoretically it's not stable for all matrices, just for most of the ones that matter practically for us. So now we're going to dive into some of the details behind Gaussian elimination with partial pivoting. I'll kind of just talk about it generally up until now. And so what is the main difference between GEPP and just GE? Well, the difference is you might decide to permute certain rows of the matrix at every step of the elimination process. And so if you remember, for GE, what we had is we found these MJ matrices, these lower triangular elementary matrices. So we found some sequence of them such that when we multiplied them by the left of A, that they upper triangularized A. Right, and so now when we consider pivoting now, or partial pivoting, what happens is when I started with A, I might have decided to permute some row, or permute two rows, right? So I have to insert now this permutation matrix P. It's an orthogonal matrix, and it's a permutation matrix. Now, and then I would go about finding this elementary matrix M, lower triangular elementary matrix, that would then zero out the first column except for the first entry of P1A. Right. So kind of the pattern now is that when I introduce pivoting, I have to introduce these orthogonal P matrices in between these M's. So the general pattern is that this will look like this, and then I'll have Pn minus 1 times Mn minus 1. And then this will upper triangularize A. So that's the difference between these two processes, is that they're generating two different sets of matrices, and the second one is a more general one, right? Because it accounts for the fact that I might be trying to pivot, or I might be trying to make a different entry a pivot instead of the one that was kind of naturally showing up had I just done Gaussian elimination with no pivoting. Okay, so here's a very simple 3x3 example to kind of walk you through what is Gaussian elimination with partial pivoting doing. So I'm going to start with this matrix A. It's a very simple 3x3 matrix. And then the first step of GEPP is I'm going to look for, or I'm going to identify the pivot. So remember, the pivot has to live in the first column because that's the one I'm trying to zero out. And what I'm trying to do is I'm trying to find the entry with the absolute, the largest absolute entry in that first column, which is 4. And then what I'm going to do is I'm not showing you what the permutation matrix is. I'm not writing it out for you, but you can figure out what it is simply because I want to interchange that second row such that it swaps to become the first row. Right? So I represent this by a permutation matrix P1 times A from the left. And what this does is it interchanges the rows. So it makes that second row now the first row. And then I'm just going to do Gaussian elimination, one step of this to zero out the all of the entries in the first column except the first one. So this is where I come up with, I find this lower triangular elementary matrix M, M1, such that when I multiply it on the left, it zeroes out everything in that first column below the pivot. Okay. So this completes one step of the GEPP process. Now I have to continue this until I get to an upper triangular matrix, right? So now we have to start with step 2. And so step 2, I'm just going to carry that matrix down from the top right to the bottom left. And then I need to identify what is the pivot. So remember, the pivot is the largest, the one I'm going to choose is I'm going to look now in the second column and find the largest entry in absolute value. But also it has to be below the first row now. Because I'm in the second column, I want to leave the first row alone. And so here in this case it's 3/4. So what I need to do is I need to take a permutation matrix P2, multiply this by the result, or what I have so far. And what this does is it will bring now that third row to be the second row. And then once I've done that, I will then proceed by doing another sweep of Gaussian elimination to basically zero out that -1/2 that was down there, to then bring me to an upper triangular matrix. So this is basically what this tells you, is that we've now, we've come up with these P's and these M's, such that we get M2, P2, M1, P1A is equal to U for an upper triangular matrix U. Right, so there's your example, kind of walking you through Gaussian elimination partial pivoting for a very simple 3x3 example. Okay, so now I want to ask another question. So before when we were not doing pivoting in the last video, basically we found these M1, M2 all the way to Mn-1, such that that they brought A into an upper triangular form. And the result was we determined that L that was showing up in the LU decomposition, we could take it to be the product of all of the inverses of these M's. However, we didn't actually have to compute these inverses directly, or even the product of the inverses directly, because these M's were so special, right? Because they are these lower triangular elementary matrices of this specific form. We were able to compute the inverses of these matrices directly by just dropping these minus signs that show up in the definition of them. And then also the product of all of them, we just basically collected entries from all of the M's. Very simply, it cost no additional flops. Once we've computed the M's, we didn't have to do any more work. So now essentially this is leading to my question, which is, but now we've changed with pivoting, we've introduced these permutation matrices, right? So we might be really worried because without pivoting, we had all these nice properties related to the M's and their inverses, and it basically let us get the LU factor very, very easily once we computed the M's. But now we have these permutation matrices P, the P1 and the P all the way to the Pn-1 that are kind of sandwiched in between. And so the question is, did we just break all of the kind of work that we did, or does it break these special properties related to the M matrices? So in other words, I want to, so given this type of decomposition, I want to figure out how do I get back to the PA is equal to LU decomposition that I told you earlier was the goal of GEPP, right? So how do I get the P and how do I get the L from this? Or is it easy or is it not easy? So the answer is yes, it is straightforward to extract the P and the L. However, there's a caveat, which is that it's not immediately obvious why it's easy, but it is. And so I'll show you on the next slide. So now I'm going to show you how do we extract the PA is equal to LU factorization. How do I extract this from this decomposition, right? So once I found these permutation matrices, and I found these elementary lower triangular matrices M, the MI and the PI, once I found them, how do I try to recollect the result to get back to this simple PA is equal to LU? So one property we're going to use to get there is if I take any of these permutation matrices, so any of the PI, and I square it, this has to be equal to the identity. So kind of the interpretation, or why, is if I permute rows in a matrix, and then I permute the same rows again, it just undoes the permutation. So it just means that P squared is the identity, right? P squared does nothing. So one thing you'll see that's very common in math is that sometimes I just choose to multiply by 1 because I can, or multiply by the identity because I can. And then later on, it seems to be useful for some reason. So this is one example of that. So what I'm going to do is I'm going to introduce a bunch of extra p's that will cancel to give me back the original result. But I'm going to introduce them and we'll see what happens. So I'm going to write that this is equal to m3 p3 m2 p3 p3 p2 m1 p2 p3 p3 p2 p1 a. So this looks pretty bizarre, or it may not be clear why I'm doing this, but I hope you believe that I can cancel this to the identity, I can cancel this to the identity, I can also cancel this to identity, and I would get back to where I was just on the line before. Okay, so once I'm at this step, I'm going to choose to just insert some parentheses to this expression. So I'm going to choose to put some parentheses here. So P3, M2, P3, P3, P2, M1, P2, P3, P3, P2, P1, A. So that's all I did is I inserted some parentheses. All right, and then I'm just going to define kind of like tilde versions of my m's. So I'm going to say this is m3. Maybe you can see where this is going. This is m2 tilde. Right, so I'm just matching. That's now this term here, but I'm not going to draw it explicitly. Times m1 tilde times a. Right, so I've kind of matched these terms. This one's here, and this one's here. So I've matched these things up, and so maybe you can kind of guess what I'm implying, or guess what's going to happen. So I have all these permutation matrices, and I now have, they've disappeared because I kind of defined these new matrices. But these m's, they are, what we can show is that they are again lower triangular elementary matrices of the exact same form, except some of their entries are permuted, right? So if you remember, all these matrices, these elementary matrices looked like the identity within one column where below the diagonal they were non-zero, or they could be non-zero. So these tilde versions of M are going to be of the exact same structure, but some of those non-zero sub-diagonal entries in that column will be permuted. And so I'm going to show you an example of this on the next slide. But that's the idea, is we can show that this is all the case. And then at this point, the question that I'm asking, how do I get back the PA-LU factor? We've kind of essentially reduced this back to the Gaussian elimination case, right? So we had the inverses of the M's were easy to get, and then the products of these inverses was also easy to get because I had these lower triangular elementary matrices, and kind of the claim is that these are also lower triangular elementary matrices of the same form that will then allow us to then recollect everything nicely and get the PA is equal to LU factorization. So let's go to the next slide, and we'll talk about I'll try to give you an argument for why this can be done. Okay, so I'm going to walk you through what happens to one of these M tildes that we just talked about on the previous slide. I'm just going to show you one of them, and then probably you'll work with a couple of them on the problem set. Maybe you'll show something similar to what I'm showing you here. All right, so that M2 looked like P3 times M2 times P3. And so what I want to see is what happens to the result, right? Or what does this matrix actually look like? So M2, right? So it's going to look like this this type of lower triangular elementary matrix. P3, there's actually only two choices for what P3 could be. right? Because the P3 cannot permute the first two rows because of how it arose in the calculation. At the step that it's at, I'm only going to look for pivots that are below the proposed pivot position or anything less, or any row less than it. So when I get to P3, basically I'm not allowed to touch the first two rows. So the 1 and the 1 have to be here. So I could either look at the one that I'm showing you, which is then the next two rows are 1 and 1, or the only other permutation matrix would have been to put a 1 here and a 1 here and a 0 here and a 0 here, but then this is just the identity matrix and it's boring. So I'm showing you that of the two cases, the one that is like not trivial is what I'm showing you here. Okay. So, okay. I'm going to take P3, P2, P3. I'm going to start multiplying it out, right? So P3 times M2, looking at how it looks like here, what it does is it just swaps the fourth in the third row, right? That's all that P3 does. So I can basically, this matrix here is equal to P3 times M2. So I swapped the third and the fourth rows to get here. Okay, so now I'm going to show you kind of what happens to these M tildes. I'm only going to show you one case. Maybe on a problem set you might look at some of the other ones, or we'll see. But so, from the previous slide, M2 tilde was equal to P3, P2, P3, where the P3 is a permutation matrix. Right, and so remember, M2, by definition of these lower triangular elementary matrices, is that it has to look like this form, right, for some Z1 and Z2. I'm just calling them constants Z1, Z2. And then, right, for the permutation matrix, one thing to note is that it has to have a 1 and a 1 here, right? So I'm showing you one example of a P3 that I could choose. It's not the only one that I might choose. It depends on where the pivot was or wasn't, right? The one that the entry that I want to be the pivot could be different, such that I would want a different permutation matrix. I just arbitrarily picked one, and I'm going to show you what happens with this choice. But really, in this case, there's only two choices I could have made, because when I'm looking in that now, the third in the next pivot position, right? So I've already done two steps of the Gaussian elimination. I can only play around with the bottom two rows, right? I'm not allowed to touch the first two in this permutation, because that's just based off of where the entries that I look for the pivot in, right, or the candidate for the pivot. Now so I'm showing you the case where I swapped the fourth in the third row, right? I could have also instead chosen the example where I have 1 and 1 here, but then this whole matrix is just the identity, and then it's boring, right? So I've just chosen to show you the interesting case of this. Okay, so what happens? I have this P3 M2 P3, and right. So I'm just going to go ahead and compute out what does P3 times M2 give you. Right. So it swaps the fourth and the third row, which is what I've done here. Right. So that's shown here. Now, you could do the matrix product algorithm to compute this, but I'm lazy. So I'm going to try to do a trick where I write the product of the two matrices as the transpose of the products of their transpose reversed, right? So this is basically saying that AB is equal to B transpose A transpose transpose. And the reason I did that is because I know that the P3 is symmetric, right? So looking here, P3 is symmetric, which means that this P3 transpose is actually just P3. And so what it's going to do is it's going to swap the third and the fourth row again. So that's how I wind up here, is I have this matrix transposed because I use that trick. You could just multiply it out, but I'm just trying to get there as quickly as possible in ways that I know how. Okay, and then you transpose it at the end, and you wind up with this matrix. Now, the thing to note is that it is of the same form as M2, right? So this is why I'm also calling it M2 with a tilde, right? Is because it has the exact same structure, but the only thing that's changed is that the entries here have been swapped. So in general, it takes some effort to show this because I've just shown you for one case and for one permutation. But in general, all of these MJ tildes, they have the same structure as the MJs without the tildes, but some of these entries below the main diagonal have been swapped, or they've been permuted themselves. And so that's kind of, and it's not a proof, but it's kind of evidence for you for what's happening here, or what's the idea with these M2 tildes, these M3 tildes, is they are just, again, elementary lower triangular matrices of the same form, but then a couple of these entries have been permuted, so that we can do the same things we did with them in the Gaussian elimination case with no pivoting. Right, so to summarize what we just discussed, so in general, GEPP will give you a factorization of this form, right? So you do your sequence of permutations and then your elementary lower triangular transformations that will zero out these entries that we want to in the matrix. And then I've also kind of just given you this argument as to why you can rewrite that decomposition in terms of this now, right? So these tilde versions of M that look exactly like the MJs, except with some of these entries permuted. And then kind of the same argument that we made in the last lecture, what happens is that we can take L to be the product of the inverses of all of these tilde M's. And then again, at the end of the day, we will just collect the entries by reading off the entries of the M, right? So if you remember, the idea was for MJ inverse, we basically take that matrix, take the same one, and then just flip the signs of the subdiagonal entries. And so you'll do the exact same thing for these tilde versions of M. And then also, again, to compute the product of them, you'll just kind of take all their entries and squash it all into one matrix, like I showed you in the last video. Right. So finally, I'm going to go over Gaussian elimination with complete pivoting. Right, so you can view this as kind of a more full-fledged version of just partial pivoting. We're going all the way. So what does this mean in the sense that it's complete? So with partial pivoting, let me try to draw a picture for what we did. So I'm going to pretend that we've already zeroed out the first, all the entries in the first column below the first one. So we've already done maybe one sweep of Gaussian elimination. Right, and so then before we do another sweep, we then have to look at, we have this submatrix, and we have an entry that lives here. Now that would be like maybe the native pivot that is there, but it may not be the one that we want, right? Because with partial pivoting, we are going to look down all of the remaining rows in that column, right? So we're going to look through all of these entries, and we're going to try to find the one that is the largest in absolute value. And then what we do is we then want to bring that entry into the pivot position, right? So say that it was the bottom one. We would then take this bottom row and we would swap it, right? So we would bring this one up there, we would bring the other one down there. And that's how we would bring this into the pivot position, right? So once it's in the pivot position, we then do Gaussian elimination, in which case we would zero out everything below. So what is Gaussian elimination with complete pivoting? With partial pivoting, we only look down that column that we were in, right? With complete pivoting, you're going to look through the entire remaining submatrix, right? So you're going to look through this entire submatrix here, and you're going to find the largest entry in absolute value over this entire submatrix, right? So, I mean, the idea is, let's say that the pivot, or let's say that the largest entry that we find, I want to get rid of that green. Let's say that the largest entry that we find is the bottom right corner, right? So if I look in that whole submatrix, the bottom right corner is the one that is the largest. I need to somehow get this entry, I need to get it all the way up into the pivot position up there, right? So it's got to travel kind of a far distance, but how do we get there? Well, I have to swap this row, right, with this row. I have to swap those, but I also have to move the columns too, right? I have to swap this column with this column. So, and let me kind of write this out in a matrix form. So with partial pivoting, you might need a permutation of the columns, sorry, a permutation of the rows of A, that then you are able to LU factor it successfully, right? And that was GEPP. But now with complete pivoting, how do we represent the fact that we also might need to pivot we also might need to swap the columns as well instead of the rows, or in addition to the rows, that's why we need this extra Q matrix that I think you may have seen earlier when I showed this. So this is I guess I would say that this is a row permutation, but this one is a column. What it does is it permutes the columns of A. So column permutation. And essentially that's the difference. So that's all that complete pivoting is you're going to look over the entire remaining submatrix, and then those are where your candidates for the pivot position live. So in the next slide, I'm going to kind of walk you through an example of doing this for a matrix so you can see it. Kind of the moral of the story is that Gaussian elimination with complete pivoting is, I think I mentioned this earlier, it's the only stable algorithm that is provably stable for all matrices, all invertible square matrices. So remember, partial pivoting, it was stable for most matrices, at least usually all the ones that we care about, but for complete pivoting, this is the algorithm, GECP. This is the one that is provably stable for all invertible square matrices. All right, so let's look at an example. So here's an example of performing Gaussian elimination with complete pivoting for just a simple 3x3 matrix. So what is the first step? We have to identify the pivot, or at least the entry that we want to be the pivot. Now, like I said, we looked through the entire submatrix, but in this case, we haven't done anything yet. We're at the very first step, so the submatrix we look over is the entire matrix. And what we want to do is we want to find the entry with the largest magnitude, right? Which in this case is that 3, right? So we're going to identify the 3 as the pivot. Now the reason, like, how this is different than partial pivoting is partial pivoting, we would have only looked in the very first column, right? So our only choices would have been either that 1 in the second row or the 1 in the third row. But now, because we're doing complete pivoting, we're able to look over the entire matrix, and we would pick the 3. But we need to get that 3 up into the pivot position, right, which is where that 0 is. So how will we do that? Is we have to do both a row interchange and a column interchange, right? So remember the P's on the left, they're encoding the row interchanging, and then the Qs on the right are they're encoding the column interchanges. So I haven't written out what the P and the Q are, but you can figure out what they are because they're just the permutation matrices that will swap these rows and columns. Right, and then what's the next step is we will just do one sweep of Gaussian elimination. So we will take that pivot now that's up there in that column, and we will use it to zero out the entries below it. All right, so then what's the next step? We need to identify the next pivot, right? So remember, we have to look over now the submatrix that excludes the first row and the first column because we don't want to touch those anymore, right? So basically, after the kth step, we exclude the first k rows and the first k columns, and we only look over that remaining submatrix. Which in this case, we look at that 2x2 submatrix, and we oh, 2/3 is the one with the largest magnitude, and so we want to now take that 2/3 and bring it into the pivot position. So you can do this by using another row interchange and then another column interchange. And that's how you get to 2/3 into the pivot position. And finally, you just end this with one final sweep of Gaussian elimination, and ta-da, you have arrived at upper triangular matrix. And what you can say is that this upper triangular matrix U is equal to M2, P2, M1, P1, A, Q1, Q2. And then kind of following these same types of arguments that I made earlier in the video, it's a little bit of work to go figure out, but you can show how you can basically read off from these M's and these P's and these Q's that we've computed. You could piece together what is the PAQ equals LU factorization, right? Which is what the Gaussian elimination with complete pivoting algorithm will produce, right? So remember, for complete pivoting, you end up with two orthogonal matrices, orthogonal permutation matrices, one that's encoding the column interchanges and one that's encoding the row interchanges. Yep. Whereas for partial pivoting, you only have the P, right? So you never are interchanging the columns. Yep. So I hope you liked the summary on Gaussian elimination with pivoting for this class.